Thanks very much to Arnold and Aldis for the invitation to tell you a little bit about our facility. It's a national lab in Stockholm, Sweden. And one of the main things we got money for to build this facility is that we can effectively store oppositely charged ions, so both cations and anions, and actually get them to merge collinearly. So you can imagine if you have a car crash, we have a car moving at 70 kilometers an hour to the left, 170 kilometers an hour to the right. That's 140 kilometers an hour collision. That's a high energy collision. Whereas in our experiment, what we can do is we can take the same fast 70 kilometers an hour ions and actually get them to merge collinearly, which means the relative collision energy can be very small. So in principle, we can go down to a zero EV collision with high energy ion bond. And then, of course, we can make use of the fact of kinematics, that the neutral particles formed, let's say by a charge exchange, they move forward at 70 kilometers an hour and hit our detector. So effectively, we can look at this low energy collision using high energy ion beams. That's what I'm going to tell you a little about today. An application does have some photonics applications and also is a little bit related to space science. I'm going to try and look at the reason why we have air glows and also sprite activity, which is something which has only been known about for the last 60 years, where after a lightning strike, occasionally you get upwards moving flares. And we still don't know what's happening and what's giving rise to these. But the reason why it's interesting is that there was a local increase of anion and ion densities by about 10 to the 6, 10 to the 7. So these are very much non-local thermal equilibrium processes, which means the standard atmospheric chemistry, the ion chemistry, has not had a chance to recover. So these are all very much non-thermal equilibrium properties and processes going on, and we still don't know what's going on. So I'm going to give you a little bit of clue about what's going on here. So as with Henrik, I'm going to first say a little bit about the people involved. So Matthias, since we also heard about how important it is to have students. So we have a whole bunch of students and postdocs and technical staff working at the facility to try and get a new generation of scientists trained up so that they can then leave our facility, leave our lab, and go and start up new areas of science elsewhere. So this work I'm going to talk about was effectively done by my student, Matthias, and we had a collaboration effectively with a postdoc now in UC Leuven in Belgium, Arnaud, and I have a collaboration with the Air Force Research Lab in the US through their European office. So these are all people who are interested in these atmospheric processes for fundamental reasons. So as with Henrik, I'm going to give you my take-home message first, which is about this reaction of charge exchange between the positive ion and the negative ion. So even though this has been known, the reaction itself for 100 years or so, no one has ever been able to measure the dynamics or the useful products in this. The only thing that people have been able to do is measure the decrease of ions as a function of collision energy or something like that, but they don't know what the products are. And of course, in a lot of cases, they don't know what the internal state of the ions was before they reacted. This is why storage ring is extremely important. So the take-home message, the first one is we've been able to measure the products and the reaction dynamics for this particular process for the first time using atmospheric diatomic cations with a key O- ion. All these things are present in these flares and these regions of air glow. The reaction dynamics for this particular anion appear to be quite similar. So the O- transfers the electron at quite far distance, typically 35 Bohr radii, and then goes away. It goes to the pub. It doesn't care anything more about the reaction at all. All the dynamics of the reaction is then given by the capture state in the diatomic molecule. And if it's a really high Rydberg state, these can then couple out to dissociative states. And what we see for a few of these systems is that all that happens. This exciting molecule falls apart. And that's really important because, of course, you're going to get 3 atomic products. And of course, we can then try and measure these things. So I say that, however, this may not always be true. We are starting to see with a few systems, there may be stable molecules formed for the product, which is not the same if you take a molecular cation and you add a free electron to it, dissociative recombination, which is another important process. In that case, the molecule always breaks apart. So in this reaction, or some of these, which I will not talk about, the molecule can actually stay stable, which is, of course, becomes a really interesting thing. And we can try and understand what's going on. So the question is, how do we get there? How do we get to these particular take-home messages? Then I'll give a brief introduction of the facility. Henrik has also mentioned it, Ulrich also mentioned it. The application to cool atmospheric plasmas and air glows, how we acquire the data, how we analyze it, and then some future ideas. So it's a facility. So we have to have a way of producing ions. So Henrik talked a little bit about positive ions. Ulrich talked a little bit about negative ions. And of course, these only use one of these two rings which are available, which is fine. And the reason why they can store their ions for many tens of seconds to many hours is this thing is cryogenically cooled. So it's about 15 Kelvin. It's basically a big double-wall vacuum vessel where we cool the inner chamber with 4 cryocoolers. So it's about 15 Kelvin on average. And the neutral particle density that's left when you pump everything out is about a few thousand per cubic centimeter. And in principle, it's like space. So you can have ions stored in there for literally days before they will be lost by collisions with a residual gas or by the fact that we cannot keep our power supply so stable over so long. You have a whole bunch of different types of ion sources to address exactly what the last 2 speakers have talked about. Making the ions is very important. We have a whole range of things that we can do. We have a high energy platform, a low energy platform, and various different ways in which we can make ions, and then we can inject them into this facility. Now, if you're using just one of the storage rings of the 2 available, it doesn't matter which one you stick them to. There are some limitations because only some lasers are in principle coupled to one of the rings, so it might be a limitation for that case. But if we want to use both rings, which we will do for a positive negative ion interaction, then of course we have some basically technical limitations for what we can do. I will come back to that in a few minutes. All right. So the motivation is cool atmospheric plasmas, air glows, sprites, and non-LT behavior. So these air glows that you see here, you see this molecular oxygen in the green, the atomic oxygen in red, and the sodium from yellow. These do not come from interactions, for example, of the atoms, the molecules in the atmosphere with the solar wind. And they do not come from aurora either. These are completely decoupled from those processes. So the question is, of course, how do they arise? So, of course, you could look in the atmosphere, for example, UV air glow, about 300 to 400 kilometers. If you look at the ion density, this is purely an atomic physics process. This is only involving ions like O plus, O minus, N plus, O minus. So we can study those, but what's the fun thing is when you start to come down in the atmosphere, molecules start to become important. And the reason why the sprites are important, if you look at the ion density around 80K, the ion density is only about 1,000 per cubic centimeter. So ion processes are not necessarily that important per se, but once you have a lightning strike and you see these flares coming up, these sprites, the temporary anion density becomes 10 to the 11 per cubic meter. So it's about 1 million to 10 million times higher than normal. So now, of course, ion-ion processes become very interesting and very important. But of course, these sprite features, they only last between tens of seconds, and then they've got, of course, collisions will get rid of anything that's going on. But what's giving rise to these photons? We want to try and understand these things. All right, so let's take a molecular cation and an atomic anion. We basically have 2 classes of outcomes. We can make a stable molecule, XY, probably in an excited state, or this thing can fragment. You can break that molecular bond and you can form 3 atoms. This gives rise to 2 sets of processes. With excited products, you can get excitation, which gives rise to these air glows in the fluorescence, because what these are a particular quantum process that you can definitely calculate the energy of those photons for. But if this reaction energy goes into kinetic energy of the fragments, this can then lead to escape. You know that outside the Earth's orbit, there's effectively a big oxygen corona. This is coming from basically oxygen atoms which are leaving that space from kinetic energy. And you can give rise to also isotope differences between, let's say, the Martian nitrogen isotope exchange between N14 and N15. This comes from collisions where N2 plus captures an electron, and the N14, that travels a little quicker. The N14 is a little faster, a little slower, so it doesn't escape the Martian atmosphere. N14 leaves. So it can give rise to atmospheric isotope differences if you give the energy to the kinetic energy of the fragments. So the physics question is, do you see a 2-body product channel, which would be the first one, or a 3-body product channel, which is the second one? Do you break this molecular bond or not? So the typical atmospheric ions, which we are looking at these altitudes, are things like O plus, N plus, O2 plus, NO plus, N2 plus, so forth and so on. The anions, which are at least going to be relatively interesting, are O minus, NO2 minus, O3 minus, so forth and so on. So I'm going to focus on today just O2 plus and O minus, just as an example. We had a paper published last year in PRL, but this is the first time anyone had ever measured the products from this reaction. So of course, there's some interest in what we can do, and I will guide you through how we got. So you've seen this picture before from Henrik. So we have the two rings. There's some difference in the construction of the rings. You see the differences in the position of the quadrupoles. This is just to do with the fact that we have positive ions in one ring and negative ions in the other ring. Only one of the rings can define the common deflection elements. So this is set such that the ions in the symmetric ring actually have the right voltage. So they will be stored, whereas the voltage on that deflector would not necessarily be the right one to bring the ion in the asymmetric ring back into its storage condition. So they have extra deflectors, and the quadrupoles are slightly positioned asymmetrically because we need to correct the ion. First thing, we have about a few hundred to a few thousand particles per cubic centimeter. It's about 15 Kelvin inside of there, so we can store things for a long time, and we can look at the products from this reaction. So we have two ions coming in here. One's going this way, one's going that way, which means any interaction in this region is going to give rise to neutrals moving this way with fairly high energy, and that's going to hit our detector. So how do we do that? In this merging beam is actually a set of drift tubes, which can be independently controlled from the outside. So we just look at this in detail. 7 elements. We have pickup charge. We have ion pickups on either side, so we can look at how our two ion beams are being overlapped. And then we take the case of a 7.5 kV O minus beam and a 17.5 kV O2 plus beam. If there's an interaction between these two beams in this region, which is grounded, the relative collision energy is 32 electrons. And then the relative time difference between when the neutral particles would arrive at our detector is typically more than 200 nanoseconds. However, once they get into this drift region where we can apply, let's say, 840 volts, positive volt slows down the positive ion beam, accelerates the negative ion beam, we can adjust the relative collision energy. But we can get down to a collision energy of around 0 eV. Now, the relative time difference between the neutral particles at our detector is less than 200 nanoseconds, typically much less than 100. So all we need to do is to measure the arrival time difference of the neutral particles at our detector and their position. Once we have that, we have the kinetic energy that was given to the factor. So we can work out what went on in this reaction. All right, so our detector is effectively a triple stack of MCPs, which have been specially made to work in 14 Kelvin. The electron cloud you get at the back end, smack it into a phosphor screen. We couple the light out from this 14 Kelvin environment, and we basically focus everything now onto a single photon counting optical detector, which effectively is an array of individually accessible PMTs. So if they're hit by a phosphor screen from the photons, we get a nice rise and decay of those PMT signals. If we have two flashes, for example, we will be able to extract the position and the difference in the arrival time between these two particles. So we can calculate the relative kinetic energy given to those fragments in the case of two-body fragmentation. In the case of 3 particles, we have to apply a little bit more maths to work out which particle was which, but we can do that by looking at ion beam overlaps, and we can extract a parameter which again is related to the kinetic energy given to those fragments. So we can work out exactly where those 3 particles came from. All right, so the question we wanted to answer was effectively what happens if we take O2 plus and react it with O minus. We get these 2 different types of outcome channels, O2 plus O, or O plus O plus O, so the molecule can stay stable, or it fragments into 3. What do we see for a low energy collision? Well, this is below, let's say, 50 millivolts collision, which is exactly related to the atmospheric conditions that these things would appear in. This molecule never stays together. It always breaks up. We see 3 atomic products, 3 channels of 3 atomic products, all in the ground state. one case where one of the atoms coming from the O2 is excited into the singlet D state, and then one channel where they're both in singlet D. Now, of course, singlet D would give rise to photon emission. So the question is, how much? Okay, it's not so much. I mean, mostly you're forming ground state oxygen, but it is some. What's really interesting is that the area under these peaks, which is kinetic energy given to the fragments, that's coming from the internal energy of the O2 plus the collision energy, plus the length of the interaction region. This could be nicely fit by a Boltzmann distribution. So our ions are low vibrationally hot. They're about 2000 Kelvin, something like that. However, this upper peak, which is appearing at the lowest kinetic energy release, this cannot be fit by a Boltzmann distribution. This is non-Boltzmann-like behavior. So something weird is happening in this particular channel. What can we do in an ion storage ring? Oh, sorry, that seems to... Okay, I will come back to this in a second. Yeah, so how do we extract information from this? Since we have three particles, we want to look at the correlation of their kinetic energies, because that's going to tell us if this interaction was a one-step process, i.e. the electron got transferred and then immediately things fall apart, or whether the electron gets transferred and the molecule takes its time before falling apart. We can look at the correlation the energies get from this interaction. So we take the energies, we calculate the fraction they get from the total kinetic energy, and we plot this in basically a two-dimensional plot, where the length along these three axes tells us how much energy that particular fragment got with respect to the total available. It gives you information about the geometry of the molecule as it broke apart. We see basically straight lines. And this is telling us immediately that this reaction is a two-step process, i.e., first the electron gets transferred, and you form an oxygen neutral atom and an O2 molecule, an O2 molecule, which then at some point later couples out to a dissociative state. What we can do is effectively back out the initial interaction. So the first time the electron gets transferred, that's a 2-1 breakup, in the sense that this gets 1/3 of the total kinetic energy, this gets 2/3, and we can effectively calculate what that state is. We can work out where on the diagram or where on the potential energy surface these reactions happen. So we take these energies or these particles, we work out their kinetic energies, we work out which state or which intermediate state they couple to. So it's either going to be 3 pi lambda u or 3 s sigma g. We can look at those states in O2 and we can work out the capture state of that electron as it was transferred. And what's the really interesting thing is that if you look at where the potentials are, this O singlet D state, which is the one which was the very small one with the non-Maxwell Boltzmann distribution, this effectively has a massive barrier. So if you have vibrationally cold ions, so if you're in the ground state and you basically capture down to this state, you're not going to be able to escape down to this channel. You're going to have to go a different way. So this presents a barrier on the exit channel. So as the ions cool down, this state goes away, which is kind of cool. So what we can do is we can do Monte Carlo simulations of these final energy vectors that these three products have got. If they were to capture into the 3 pi lambda u state, the 3 s sigma g state, we can combine them and then compare them to experiment. And this was just accepted into Nature Communications. All right, so what can we do next? As a summary, we can develop further the utility of this facility. We can make use of the fact that we can store ions for many tens of seconds. Unfortunately, we can't store them for many hours if we have 2 ions at the same time. We can store them for tens of seconds. We can look at cooling-dependent dynamics. We can follow the reaction dynamics. We can look at the intermediate capture states, and we can calculate quantum yields. We can do channel blocking. We can do chemistry. So if you think about the electron donor, then of course you pay more to take the electron from certain elements, as we heard from Otis. I mean, some of these, like fluorine or chlorine, are several electron volts of energy. Sometimes then, if the payment is too high, then the fragmentation of the diatomic molecule the electron is being transferred to cannot happen. you capture into a state below the dissociation number. So then the molecule has to be stable. So then, of course, we're going to start to look a little bit at that. All right. So to summarize, DESIREE is an infrastructure facility, which means twice a year we have calls for beam time. And I encourage you to contact me. Our oldest has already been through this process, so he knows about what you have to do. It's funded by quite a few funding agencies. And again, to remind you about the take-home message is that we're able to measure for the first time products and dynamics from this particular interaction. They seem to be fairly similar, although maybe if I come again to the next meeting, I can tell you about reactions that don't look this way, which is also kind of more interesting. But we're also trying to work out simple models to try and explain these dynamics. All right, I'm done. Thanks very much for your attention.